web search queries. Now, I've heard a lot of things about anchor text. If you know about ranking and weighting, you should weight anchor text real low. There's also adversarial IR, right? There's spammers, there's bad guys that try to fool the system. They try to be on top for any query to just to make money or to game the system. And there's also monetization. This is a big thing, right? Even this thing gave rise to a whole sub-discipline or discipline, whatever you want to call it, is computational advertising, which is how to serve the best ads possible for a user given a query or given a page, right? That would be contextual advertising. And these are new paradigms, tasks that come with the web. Now, user needs on the web. Again, something else that Andre came up with. He said, well, there are three main user needs on the web. There are many more than that, but this is a very, very broad classification of those. So informational queries, when you want to learn about something, right? So for instance, low hemoglobin. Navigational queries. You want to go to a particular site, like United Airlines. Now, you will be amazed how many people, when they want to go to Yahoo, Google, or Facebook, they type Facebook in Google. And then they click on the first result. So this is a navigational query. I've seen people type in Google on Google and click on the first result. Just it's like a meta-navigational mistake, right? Third big type, transactional. So you want to do something online, right? You want to access a service, like book a flight. Or you want to download something like a song or a picture. Or you want to buy something. So these are transactional queries. Like Seattle weather, Mars surface images, or Canon 6410. But there's much more to this. Right? There's much more to this. It's just trying to frame us into these three big categories, especially since 2001, where now we can do a crazy new amount of new things on the web. It's not going to work. So there's some studies on that, like intent and that, and you can learn about that more. But these are, widely accepted taxonomy of web search. The numbers are the percentage of queries that fall into this category. Now, this was done in 2001. I don't want to believe this by heart. I mean, I'm not mentioning them because, I'm stealing blatantly the slide, but possibly this doesn't hold anymore, right? But yeah, I mean, you see it's more or less 40, 25, 35. It's not like a big difference. Right. Failure. Failure is very important, knowing that you're not delivering the right results in a web search scenario, because people do not go through a lot of results, right? They just stop at the first or the second page. So this pie was taken in 2006, and it said when you perform a search on a search engine and find what you're looking for, at what point you typically either revise your search or move on to another search engine. So it says 25% says after the first page, 16% is after the first entry, so you don't even go through the first 10 results at all. And then more than 3 pages, only 12%. So you really need to be very precise, even though there's a lot of potential candidates to a particular query. So users are central also in web search. And I hope you learn more about this on Saturday during George's talk. So this is the cool part about it. So I can just tell you all the problems, and I don't have to explain how you solve them, because he's going to do it. But quality of pages, it varies widely. Relevance, as we discussed in the beginning, it might not be enough. You might need more things to say that something is better than something else. So, other desirable qualities. You can have content, web readability, that the page doesn't have pop-ups or flashy ads. This is, IR doesn't care about this. But a web search designer maybe should. Precision against recall, right? So precision, again, you'll learn more about this, is how good you are in solving this user's query, and recall is how many good documents can you surface for a particular query. And there's a tension between those. There's always a trade-off. You can be very precise, but completely fail at recall, and the opposite. And it's like a scale, right? they go one with the other. Said on the web, recall seldom matters. So as we saw in the pie chart before. But then what matters, right? The first result, the first 10 results, just to be good at the head queries, the queries that people submit continuously, being good at all the queries. So something that is interesting is that we are all very similar and we're all very unique. So we're all very similar because a lot of the common queries we all submit. Right? So we issue the same queries, believe it or not. But then there's these particular rare queries that only you submit. So we're all very similar and very different at the same time. And you have to be good at both types of queries. You cannot just be good at head queries. That's never going to work. I remember this new Italian search engine that came up this year, and they let me try it before it was open to the public. And I said, well, this is not going to work because people are going to look for themselves, and you're not finding any of me or my friends or people I know. So this is going to suck completely. So these things matter a lot in web search. Now, when you're quantifying IR performance, maybe it doesn't matter that much. You want like an average, especially in research papers. And then again, we're always dealing with users' perceptions, right? Which might be non-scientific. But if you start aggregate user perceptions over a large amount of people and starting to care about whether people find what they need quickly or not, then this is already meaningful, right, and significant. So again, relevance and results are valid or not, if the UI is simple, if you're error tolerant, we talk about this. Right? If results are objective, if you want opinionated results, if you have an ambiguous query, are you actually covering all the possible topics that the query spans, right? The Jaguar or Apple, right? What things do you display? So are you displaying all the possible topics? There's one narrow topic. Are you covering everything or not? There's also a lot of tools that we're now very used to use them, like auto spell check, spell assistance, query suggestions, like things like search within results, more like this, refined. And all that seems pretty natural to us, but before people came up with these tools and thought that this was possible, then nobody was doing that. And then, of course, the web. The web is just crazy. So you need to deal with specific vocabulary, which has an impact on everything you do. And for instance, I mean, people that type URLs on the search box, what do you do with that? So there's, this kind of crazy behavior that can show up in a search engine. Or queries like, what is the last, the best, and the worst, blah. You solve that. But you send them to Yahoo Answers. Very quickly, because you don't have this distributed lecture anymore, so crawling. I'm going to be talking about crawling. But first, the web. So the web has no design. The web has no coordination. And the way is democratic, because you can publish mostly whatever you want. There are some restrictions on the top, but there's a lot of content there, and nobody controls what's put in there, more or less. But you don't control when somebody's going to create a new page, or is going to delete an existing page, or link to another page. All that happens out of the sudden, and you need to somehow anticipate all that. Content has truth, lies, obsolete information, contradictions, unstructured text, HTML, semi-structure, JSON, XML, RDF, structure, so it even has database results, tables. And, this is like, again, a scale blow up. And at the beginning, people say that this is going to grow, the volume of web pages is going to grow twice in a few months. And it's not quite the case, because we will be like on the universe y-axis already. But it's still expanding. I think something like Twitter or Facebook now with user-generated content is getting even more complicated. Because content can be dynamically generated as well. You can have pages that create new pages on the fly. So a crawler, again, the crawler is the program that goes on the web and starts tracking web pages and pulling the web pages into your storage for further processing. So what is the basic crawler operation? So you have a known seed of URLs. So you know that these sites are there, and you start there. You go and you fetch these pages, you parse the pages, and you just get the links. So who are you pointing to? And you put this on a queue, right? And then you start getting things on the queue and repeat. And you put more stuff on the queue, and put more stuff on the queue, and then start crawling things around. And that looks like a nice story, but of course it's much more complicated than that. But what you have is, this ugly circle is the web. You have your seed pages, and your crawler is the spider here, and there's a lot of stuff you haven't seen. Now you crawl these URLs here, you parse them, so you've seen this part of the web. Right? And this is the things you're pointing at. That you have this covered, but you haven't fetched yet. So things that will be on the queue. Okay? And you just need to advance. Now, well, complications. First of all, you cannot use just one machine. Depending on what is the domain. I mean, you want to crawl just a particular host or just 10 million pages, maybe you can survive with a machine. But all these above steps, in general, are distributed. They are spanned through a range of machines. And then distribution is always a synonym of complication. But anyway, there are malicious pages. So there are spam pages, things that want you to iterate over the same set of pages over and over again. Spider traps. So you can have a web page that is http foo.com/foo/com/foo/com, and you can create an infinite amount of links every time because it knows where you're coming from. So if you don't take into account that, then the crawler is going to be just stuck there. And even if the page is not malicious, then there are also challenges, right? So the latency and the bandwidth of these sites, it's different, it varies. And also webmasters might say, well, I don't want you to crawl these pages at all, right? So you have to respect that. There's also duplicate pages. There's also mirrors. You don't want to spend your time going into these pages that you've seen already. So now that maybe, okay, just keep a copy of those. And how do you do web scale duplicate detection, right? Online? This is very tricky. Also, you have to be polite. You cannot just hit a host very often, right? You can take it down. So you need to respect this. These are the rules of the game. So what you must do, again, be polite, respect the pages, don't hit the server too hard, and only crawl allowed pages. So there's this robots.txt file on every host that says, well, you can crawl these pages if you are this guy, right? Or if you are this guy, don't crawl the pages. And you have to respect this. You have to be robust. You cannot fall into these spider traps. You cannot be caught into this malicious behavior from web servers. And you have to be efficient. I mean, you really want to be using all your resources as much as you can. Right? What you should do is be distributed. So a lot of machines talking to each other. Be scalable. So again, scalable is all about, you have to do this task. If you put more machines, then you're going to be faster, right? And then performance and efficiency. So, permit the full use of all the processing capabilities you have and all the network bandwidth that you have. What you should do, and this is another challenge, is that you need to get pages of high quality first. And high quality is something that is application dependent. So I guess there's no universal definition of what a high quality page is. So for a new site, it might be different than for a general search engine or an image search engine. And you have to do it continuously. So that's the thing, right? So changes occur all the time. Pages are dynamically updated, and you need to reflect this content. So I don't know how many of you remember, but I think back in 2004, 2005, Google only refreshed its index once per month. And people were waiting, no, I'm waiting for Google's refresh to get my content updated. Now this is happening in seconds, right? You put something new on a page, and if you're high quality, immediately there. And the first time I knew how they were doing, I was amazed. Mesmerized by how can we go from one paradigm to the other. And this is all user desire driven. Also, you need to adapt to new formats, new protocols. You have to be able to do all kind of content, right? Then, if you have distributed crawler, this is what happens. Essentially, you have your frontier, which is a shared queue between all these crawling threads, and you sort of need to coordinate them so that they don't crawl the same URLs twice. All right. So much for that. Again, next block is representation, right? So how, again, reset. How does the machine see the documents? How do we index the documents? How do we tell the machine, this is what I want to store? So this is a kind of Spartan slide. This is the document here, sailing in Greece. And we have a lot of views here. So one is the content view, which is just the words. Okay? Just what the document is about. There's the data view. This is more like the author, the creation date of the page, the last time it has been updated. More like a database style kind of view of the page. There's also the structure view, right? What is the head of the page? What is the title? Who is the author? You have chapters, you have sections, if it was a book, for instance. And you have the layout view, which is how does the user see the page. This is interesting because this is device dependent. So maybe for a mobile search engine, this is a different kind of view than for a web search engine, or desktop search engine. So quickly, content view is concerned by representing what the content, what the document is about. Data view, it's factual data that is associated with the document, and it's there, like authors, publishing dates. Layout is how documents are displayed to users, and structure has to do with the logical structure of the document. Okay? Very good. So content, the rest I won't be talking about. So in general, you want to create what you call an indexing language, which is, you can get very philosophical about it, but it's like the language that you use to describe the content of the documents and the queries, right? So the words that you use. It consists of the index term that are derived from the text. Right? This manual indexing is something from the past, unless you have a very narrow domain application that you want to put this into. But again, the only thing you need to know is that if this query term is present in this document or not. Right? This is what the function that you need to implement in your code. Then how you generate this representation. So this is not easy. Right? So how you build the indexing language has several steps. I think we'll go through some of them until we'll get bored. But first, you have to detect what is the char encoding of the page. Maybe you need to tell what language the page is written in. Maybe you want to segment the page. You want to know this is the title, this is the head, this is the body. You want to maybe know that this part of the page here is just navigational links, columns that are present in every other page in this site. So you don't want it. Or these are ads. You don't want those. That's called boilerplate detection, essentially taking away all the fat from web pages. Tokenization. So what are the individual components of the page? What are the words that you want to put in the index? What are the words that you want to search for later on? Term normalization. So of course, language is crazy, so we need to be able to represent terms in many different ways. See some of that. Stopper removal. So maybe some frequent words that you don't want to keep in the index because they don't carry any content, and even if people search for them, you don't want to surface any documents for those. And there's another, say, heuristics to try to increase the coverage of the representation of your document, such as stemming or document expansion. We'll see some examples of that. Again, a simplified version of the pipeline, right? So you get the documents, you tokenize the documents, you get tokens, which are the words. You remove the noisy words, the they, off, in, whatever. All these things you take out. This is stopper removal. And then you reduce to stems. So essentially it's like conflating the terms. Something like I don't know, internationalization to international. Right? So you chop the ending of the word. This, you don't have to do this, right? So, in web search is rather uncommon, but it sort of can bring some benefits for some languages, like Spanish. And then you get terms, and these terms you put them in the index. And then you can search for these terms later. I'll be really quick with this. So parsing a document. So what is the format of the document? Right? It's a PDF, it's a Word, it's HTML, it's Excel, it's PowerPoint. What are the languages in the document? And what is the char set in the document? So here the char set, for instance, for web pages, you might think, well, the char set is usually on the header of the page. That's not the case most of the times. So you need to deal with all these issues, and most of the time you do it heuristics. You think of a reasonable solution that's going to work for 90% of the cases, and you implement this solution. And some other more advanced solutions will incorporate some classification, some machine learning on top of this. But again, it has to be cheap. You cannot spend a lot of time doing this because you're going to do it at scale, so heuristics are fine. So, problems. Right. What happens if a document contains many languages? So that happens with most of my emails, for instance. Or, you're taking notes in class, but then there is a quote in French or in English. So what do you do with that? You run a language detector for every possible sentence of the document. You assign one language per document. You try to guess. You want to make your life easy, you do one language per document. The good news is that some open source libraries that work fairly well for language detection that you can use. And they're fairly cheap to run because they operate on the engrams of the strings, of the words. Again, what is a document? So you're thinking of web search, okay, a document is a document, it's a web page. Yeah, maybe not. So imagine you're doing desktop search. So what is a document? A file? A PowerPoint? Yeah, seems reasonable. But then what happens if an email has one attachment? What happens if the email has 5 attachments? Is each one of the attachments one document? You consider all of them as one big document? A group of files, is it one document or many, many documents? So essentially, let me see if I have this. So the thing is, if you have smaller documents, so imagine that you want to index sentences of web pages, and you want to display to the user sentences and not whole documents. Well, if you find the right sentence, that is very good because you're bringing the user already what she wants. But again, you're missing all the context of the rest of the document. And if you think how you operate, you issue a query and you want to look for this term somewhere in this document. So the chances of missing the term, if you just index the sentences, are higher. So there's always a tension between how good you're going to be at displaying results and how comprehensive you can be. Right? Precision and recall again. So real quick, so tokenization, again, you have this input, friends, coma, romance, and countrymen, and you just output these 3 tokens, right? Which is an instance of a sequence of characters. And I'm assuming you already know how to transform the bytes from a web page into a sequence of characters because you know encoding and blah, blah, blah. So now each one of these guys is a candidate for putting in your index. It's a candidate for making it into your presentation. But it might be chopped on the pipeline, right? It might be removed, so you need further process. So what are the valid tokens to emit? Because think of this problem, right? You have apostrophe S. So what you do, you split Finland and S, you put Finland's, you put this as a token, so this would be the string that you're matching to. So if you have hyphens, for instance, you split in 2 different words, you take it as the same one. What we do is essentially we tend to split this. Also San Francisco, you have 1 token or 2. This is going to be San Francisco together most of the times. Essentially, I mean, this might look like a big problem. Once you have proximity information, if you can tell which words were occurring together in a document when you retrieve your web pages or whatever, this is not a problem anymore because you can sort of recover back this information. Numbers. Well, was a discussion about numbers before. So like up to like 6, 7, 8 years ago, search engines weren't indexed numbers. Now you think about them, they are super useful. Think of dates. Think of, I mean, last time your program crashed and you were looking for the stack trace. These are things that you want there, right? But often you index the numbers separately as metadata. But then again, there's the issue of normalizing. You know that this is a date, how you turn this into this or into that. And for instance, this will be good for European standards, but this will be good for American standards, or the opposite. The opposite. Anyway, I mean, and this might look boring, but really getting your tokenizer right can buy you a lot of performance. So you can have a super complex retrieval model that does magic. If this basic representation is wrong, then nothing to do. So for instance, for German, like splitting the compound. So this is a German word, as crazy as it might look like. It's life insurance company employee. You cannot pronounce it without choking if you're not German. But splitting this thing, the compound splitter, brings a lot of performance. Other languages. So for the typical example is Chinese and Japanese, right? So they don't have spaces. So how do you decide that the word should be here and here and here and here and here? Right? So you have to do prefix matching. And the thing is that many times you cannot guarantee there's a unique tokenization. Many times there's many possible interpretations of the sequence. So what you tend to do is you tend to index all of them for one document, which can lead to a significant increase of size. More issues. So languages that go from right to left. So you go from right to left, but then you have a number, and this number goes from left to right. And this is the same thing. Think of an algorithm to solve this. Right? This is pretty tough. Or maybe not, because if you use Unicode, this is already straightforward. It's already done for you in Unicode. Somebody had the great idea to make the representation already uniform, so that's not a problem. So the store form is already straightforward. But we could be talking about these things forever. I mean, you could teach me a lot of things about maybe Indie that I don't know about. I could be discussing for hours about what would be the best way of representing this information. Every language is different. Every script is different, and it takes a lot of engineering effort or care if you want. You really need to care about getting this thing right to get a great search engine. Now, stop words. So as I said, stop words is words that you don't like, so you just remove them. So they have very little semantic information. So you just take them out from the index. And you think about it, like around 30% of the incidences in your index, so like the entries you have, come from 30 words. And we'll see later why. But then search engines are pretty smart, and you use data compression techniques to store your index. So when you use these data compression techniques, essentially it means that you know how to store these lists in a very efficient manner. So, I mean, if you know a word occurs in every single document, you don't even need to store which documents it occurs in. You know it's all of them. Right? Or if you know it occurs in all but one, you just need to store this one. So there's very efficient ways to deal with this. So essentially, the problem of removing stop words in the system is that you cannot solve queries like the who, right? Which is a very legit query. Or phrase queries, king of Denmark. So if you remove off, then what do you do? Right? You will never know that these three words occur together in the original document. As a matter of curiosity, a lot of song titles contain only stop words. All right, normalization. So again, how do you know that USA with the dots is the same as USA? How you, essentially, like very briefly, because I'm running out of time, but what you do is you bring classes of words into the same equivalence class. You know that these two guys, they should be the same. And you have rules for telling that these two guys should be the same, like, remove this. Right? So whenever you see this guy, remove the hyphen. And then these two are going to be the same. Okay? other languages. Again, accents or apostrophes or umlauts here. So you remove them, you don't remove them. So it's very, very language specific. And so think of a company like Yahoo or Google, right? You're doing web search and you're dealing with over 70 different languages. And each one is different from the others, and each one has its own complications. So think of the amount of engineering effort it takes to understand these kind of issues. Case folding, right? So you want to downcase things, but then sometimes you don't want to downcase things. So, General Motors, maybe you want them upcase the first letter, especially if you're doing like an NER, a name entity recognizer. You might learn about this later, but they are heavily dependent on these caps. Right? So if you decide just to caps down everything, lowercase everything in your pipeline, and then you put the NER is going to fail completely. So you need to take care in what steps you do things. On the other hand, NER needs the tokens already, so how do you solve this? And this is amazing that long-standing Google example. This was fixed in 2011. This is the query CAT, which is the caterpillar. Right. The first result was lolcats until 2011. Right? So there's always going to be small nuances like this to deal with.